So in this video, we're going to talk about concavity when dealing with functions. So we can determine the concavity of a function using the second derivative test. So basically, we have some function and we find its second derivative. So I'm going to call that f double prime. And obviously, in order to do this, we have to first differentiate it once and then we differentiate that again to get to here. So when we're looking at f double prime, we consider the places where f double prime does not exist. We consider the places where f double prime equals 0. And these are going to give us our critical points for the second derivative test. So a function has a second derivative. The second derivative tells us if a function is concave up or concave down. So here, between here and up to here, about halfway up, this is concave up, and we're going to call that CU. And then from this halfway point to about, well, here it's about all the way down. So this whole point we have concave down. So notice that it's kind of like a cup and then it cups down. Okay? So it's concave down whenever f double prime is less than 0. So obviously down less than 0, that makes sense. And it's concave up whenever f double prime is greater than 0, right? Again, up greater than 0 makes sense. Now this is just something you kind of have to remember. You can go into a little bit more analysis and look at, how the first derivative gives you, the increasing, decreasing, and then how when that's increasing or decreasing, it's giving you these things. It just takes a little bit more time, and at this level, and a first year undergraduate calculus course for science students, it doesn't really make a lot of sense going into detail. Just trust me on this. So this is pretty easy. This is very similar to what we did in the last video. I don't know if you remember when we were talking about increasing, decreasing, and we looked at the critical points. Now we're just going to do it again. Obviously, a function can't, randomly go from being negative to positive or negative to positive, without either not existing or 0, because these are continuous functions. And obviously, if it's not continuous, then it doesn't exist at that point where it's not continuous. So hopefully you guys all have an understanding of continuous functions. If you don't, that's okay. Just trust me that in order to go from negative to positive, it has to pass 0 or it has to not exist at a point. So, well, how do we do this? It's really pretty simple. We just take our function. So say I have f of x is equal to x cubed plus 2x squared plus 2x plus 1, right? So I'm going to find my first derivative, and that's going to give me 3x squared plus 4x plus 2, and I'm going to take my second derivative, which is going to give me 6x plus 4, okay? So I notice that 6x plus 4 equals 0. I set it equal to 0, and I go 6x is equal to negative 4, x is equal to negative 4 divided by 6. So we have x is equal to negative 2 over 3. This is our critical point. Okay, so I don't know if you watched the previous video, you noticed that we did a sine, not a sing chart, but a sine chart. So we take, it's basically a number line, we stick our point, negative 2 over 3, and we stick points on either side. So we go negative infinity to negative 2 over 3, and we have negative 2 over 3 up to positive infinity. So we pick random points. Here I'm going to pick negative 1, and I'm going to plug that in this function. So negative 6 plus 4, well, that's going to give me negative 2, so that's negative. Here I'm going to pick 0, that's going to give me positive 4, so this is going to give me a positive number. So I know that from here to here it's concave down, and from here to here it's concave up. So concave down is like this, and concave up is like this. So we can actually put this together with the information that we had from the increasing, decreasing, and we can make this really nifty chart. Now, what color do I want to make this? So we can have concave up, and then we can have concave down. I'm going to write that as CD here. And then we can have increasing, and we can have decreasing. I'm going to write that as dec instead. So we have this little chart. Okay? So a function that is increasing and concave up, well, here's concave up, but it's going to be just the going up part. So it's going to look like this, okay? Then when it's concave down and it's increasing, well, it's going to look like this. Notice that I put them together, I would get this. So I know that whenever I'm going from concave down to concave up while still increasing, I'm going to get this local minimum thing happening, okay? So now let's look at decreasing. Let's look at, crap, I totally messed this up. Well, here. This one was supposed to be here. Sorry, I hope you can forgive me. I really don't want to make this video again. Okay, so yeah, this one was the decreasing. So whenever it's concave, it's continually concave up and we go from decreasing to increasing, we know that we're going to get this local minimum. And that was the same as what we had over here. Let me bring back our previous video. And we noticed that we had a local minimum when we went from decreasing up to increasing. Well, now we can be a little bit more sophisticated, and when we go from decreasing to increasing and concave up, then we're for sure getting this local minimum sort of cuppy curve thing. And then if we look at concave down, and we want to be increasing, so here we're going up, 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 so we're increasing, so it's going to look like this. All right, pardon my mistake earlier. I hope you all forgave me for that. And then if we're still on concave down and we're decreasing, it's going to come along this line like that, and we're going to have this function. So we know that we're going to get a local max whenever we put an increasing to decreasing and concave down, right? So with these 4 different types, so let me just remind you that these represent different different values of our function. So increasing is f prime is greater than 0. Decreasing is f prime is less than 0. Concave up is f double prime is greater than 0. And concave down is f double prime is less than 0. So with these 4 pieces of information, you can construct an entire function just by piecing them together, just by piecing these little bits together. So these let me go back to these points here. And we call these points points of inflection, or POI for short. Basically, you can't go from increasing to decreasing, or you can't go from concave up to concave down without a point of inflection. So if we come back to our little example over here, we notice that we're concave down, and then we had to switch and become concave up. And that happened at this little point, which is a POI. And they happen basically halfway between, you know, any of these points like this. They could happen at other times, but you're never going to have concave down. So using this and what we learned in the last video, we can put this all together and we can start graphing functions. In order to graph a function, first what we need to do is we need to find all critical points and points of inflection. So that means finding f prime and f double prime. Sorry, I didn't finish my word there. So f prime and f double prime. I know that's kind of hard to read. Let's zoom in a little bit. All right. Once we've done that, we can determine increasing and decreasing, and concave up and concave down. Determine. Sorry, my spelling. It's not my spelling that sucks, it's my actual handwriting that sucks. Please forgive me. All right, so we can determine the increasing, decreasing, concave up. So basically we can determine where each of these pieces falls on the graph. So while we're graphing, we put on all points. So basically you draw all the points that you need. So all the critical points, all the points of inflection, you put them on and you label them. Then you just draw in puzzle piece. And by puzzle piece, I mean these things. So you just take this and you drop it in. You're like, oh, from here to here, we know it's concave up and increasing. I'm going to stick that in. From, you know, this point to this point, I know it's going to be concave down and decreasing. So I'm going to take this thing and go in there. And it's really pretty easy. I'll do another video next time about graphing an entire function. If I don't get to that before your tutorial, good luck, we'll go over it in tutorial. And make sure you try out the practice problems listed below. Good luck!